Hello there and welcome back to this video series on control systems. Before we jump into the video, let us do a quick recap. We saw that in an open loop system, there is no measurement of the controlled variable and no feedback to the regulator. Whereas in a closed loop system, the controlled variable is measured and fed back to the regulator. After watching this video, perhaps you will be able to explain what is a comparator, indicate in standard form a closed loop system, and explain the term error. With that said, let us jump into the video by considering the example of a refrigerator. We are calling it a closed loop system, and we'll once again see what we mean when we say it is a closed loop system. We saw that there is a required temperature that is depending on what we need from the refrigerator. We turn the knob on the thermostat to a particular location. Corresponding to that setting that we give, certain amount of refrigerator is circulated in the evaporator coils and also through the entire circuit. And depending on that, you achieve a temperature inside the fridge. And this temperature inside the fridge is what we call controlled variable. This we said we can represent in the form of a block diagram shown here. The reference temperature is the temperature that we require to exist within the refrigerator. Thermostat is the setting through which we give that required temperature, and the manipulated variable, the variable which directly affects the controlled variable, is the refrigerant circulation. Depending on this, the refrigerator cycle works and a temperature is established in the refrigerator. We can see that depending on the ambient temperature, depending on the contents in the fridge, an equilibrium is established corresponding to each required temperature. We can easily see through experience that this equilibrium is maintained until and unless some kind of a disturbance comes on it to change the equilibrium. The disturbance may be either opening and closing of the fridge, or it may be change in the ambient temperature, or maybe change in the contents within the refrigerator. For now, we will consider the disturbance to be opening and closing of the refrigerator, but the discussion generally does not change when any other type of disturbance occurs. What we mean by disturbance is any outside interference that will change the equilibrium of the system. We will consider this system and try to show how the feedback path kicks in. Okay. We'll try to consider this system and try to refine it to generalize it. To begin with, we will try to show each element in a conceptual block diagram, beginning with the thermostat block. Recall that the action goes around a loop as shown here. There is a required temperature setting. The thermostat receives that. The thermostat also receives what is the temperature, actual temperature in the fridge. It will receive both, find the difference, that is what is the deviation. According to it, it will compute how much refrigerant, additional or less refrigerant, needs to be circulated, and when that goes through the system, the temperature changes, and this temperature again the thermocouple measures. So you can see that the action is going around a loop. That is the reason why we call it a closed loop system. Generally, we can see that the faster this feedback path is, the faster this closed loop system is acting. So if a disturbance is occurring at, let us say, 10 times a minute, and the feedback path is occurring 20 times a minute, that is, feedback is quick enough to catch the disturbance. I know these words are kind of loosely said, but you can understand the thing this way. When the feedback path is faster, if it is continuous, as in the case of an analog, it is ideal. Now we'll try to put it in the form of a block diagram. Okay. Conceptually, we have a component called comparator. It may be a circuit or it may be a device. This finds the difference between the reference temperature and the controlled temperature. This is what we want and this is what is existing actually. So it will find out the difference between what we want and what is existing and find out what we call an error signal. Again, note here that this is very general enough. You may remove the word temperature and put reference speed, controlled speed to get the error in the speed, or reference acceleration, controlled acceleration, and this is error in acceleration. That is what we mean when we say we are generalizing this block diagram. The idea is that as long as the error does not equal to 0, does not reach 0, the control system is not still in equilibrium. We'll look at the second block, which is a regulator. The regulator receives the error signal and gives an actuating signal. This we may call it manipulated variable also. Okay, error signal is the input to the regulator. Actuating signal, that is manipulated variable, is the output from the regulator. Okay, the idea is that the controller issues an actuating signal in response to the error. That is, in some sense, if the error is very small, the actuating signal is very small. If the error is very large, the actuating signal tends to get very large. Okay, note that these variables m and e may be related by a static equation or a differential equation. The next block that we see is the system. Okay, the actuating signal is the refrigerant circulated, and the output of this system is the controlled variable. Again, we are trying to make it very general, gradually, step by step. We may talk in terms of temperatures, or we may talk in terms of speeds or other variables, but the process going on is the same. There is one more component in a closed loop system, that is measurement. Okay, there is a thermocouple, and the thermocouple takes in the temperature and issues a voltage. This voltage is used as a measured value. We'll try to put all these things together to form an overall connected block diagram, which is shown over here. This is the comparator, this is the regulator, this is the actual system, and this is the thermocouple. You can see that the temperature is coming from right to left and coming back. That is the reason why this diagram is kind of drawn flipped. You have input at one end, output at the other end. We can see that the same error is flowing through, so we may connect both these blocks together as shown here. Similarly, the same signal is flowing through in the same direction, so we join the block at the actuating signal. Similarly, you can see that controlled variable is the temperature. The temperature is flowing back, so we may join it to form a complete block diagram of the closed loop system. You can see that the control action is flowing through in a loop. With that said, it is possible to generalize the block diagram and show it over here. This comparator as well as the regulator put together we may call a controller. With that, we can summarize this video as follows. There are 4 components in the block diagram of a closed loop system. One is a comparator, which finds the error, that is the difference between what we want and what we are getting. It may be temperature, speed, or acceleration, whatever. A regulator issues the actuating command. This sometimes may also be called the manipulated variable. And the system is the process to be controlled. Feedback is typically measurement process. And we saw that it is possible to draw a generalized closed loop block diagram. That's all we have for now. Have a great day.